The do now says define the word excluded. If you're using everyday language, excluded could mean a lot of things. But in a real everyday life, I mean, I can exclude people if I just shut the door. Yeah. So we got, I think, let's see, I think it's 3 students missing, 4 students missing. If I wanted to exclude themselves from the class, I just shut the door, lock it, and then when they knocked on the door, if they're not absent today, that would be a way to exclude them. It would be terrible, but that's a form of exclusion, all right? So you could make the decision to purposely exclude, all right? But then sometimes there's a natural exclusion, all right? So, for example, if if you live in a district, you go to the school. Typically, if you're a public school student, you go to the school in your district. All right, you would be excluded from every other district, not because they're being mean to you, but because you are included in another district. All right, so you're already included somewhere. You're already accounted for. All right, if you're a student in my class, then you would not necessarily be a student in Mr. Egler's class, as a Algebra 1 student, because you're already included somewhere. All right, it would be a double dip. All right, so that's more of the context that we're looking for here, where we would be saying not permitted to be in a numerical set due to the constraints of the algebraic expression. All right. So another way you could think of exclusion is, let's say you wanted to buy tickets to a concert, and they sell, there's 30,000 seats in the arena, and you're the 30,001st person. And like all the seats are gone. They didn't purposely exclude you. They're not being mean to you. It's just it was first come, first serve, and you weren't one of the first there. So you weren't able to get a ticket. So you're not permitted to be in that set because of the natural constraints. All right, the constraint is like the physical limitation. All right, so in this case, we'll have a constraint when it comes to the algebraic expressions, and that will dictate what numbers are allowed to be in the set and what aren't. All right, so it'll impact our closed set if we think back to closure. All right. So what type of mathematical expressions would yield an error screen on your calculator? Well, there's a few different kinds, but the ones that we're going to focus on are fractional ones. So fractions with variables in the denominator. And I'll put the S in parentheses because it could be more than one variable. Denominator. Or radicals containing variables. All right, so those are the ones that we would focus on at this point. All right, so let me bring up the good old TI. I'll show you on both calculators. So I'll do the Desmos one first. If I say 1 divided by, I'll just put in the 0 just to make it obvious. It says undefined. But if I put in some variable, I'll call it an A. You can see if I add a slider here for A, that you'll get an answer, you'll get a number answer for everything except for 0. All right, so 0 would not give you a numerical answer. So for this expression, 1 over A, 0 would be an excluded value because 0 would break the expression algebraically. All right. So I could do the same thing with a radical. Let's say I have radical A. Now in that situation, positive numbers are good. All good with the positives. Even 0 is fine for the radical. But then once you get to the negatives, it breaks the expression. Because in the real number system, we can't have negatives under radicals. It becomes imaginary. I don't know why this stray mark is showing up now. It does that sometimes on the touchscreens. All right, so for the TI, similar idea. So 1 over, let's say, I'll just type it in, 1 over 0. It'll come up with error divide by 0. It won't say undefined, as nice, it gives it a little bit of a nicer look. But it'll tell you that there's something wrong. But the problem with the TI, I mean, it's good and it's bad. Anything that will break an expression, the TI calculator is going to say error. It's your job to diagnose whether that error is a problem with something you typed in or if the error is something related to the math. All right? So if I say, for example, let me just type in something that's obviously incorrect. I'm going to type in a -6. All right? So I type it in like this, a -6, but I used a minus sign instead of a negative sign. It's going to say error syntax. Syntax is talking about the language. Right? It means I typed in something incorrectly. That one's on me. If you see syntax, you made a mistake. All right? If you see error divide by 0, or if you see error non-real answer, that means it could go either way. It's possible you typed in something incorrectly, but it's also possible that you found an excluded value. All right? Now, we have talked about both of these calculators enough for you probably to recognize that we have sliders for the the Desmos calculator, but there's no slider for the TI calculator. All right? So how would you handle that? Well, we started talking about typing in expressions into y equals yesterday. So let's do that real quick. I'm going to type in, sorry, I got to get rid of this. Pretend that was off to begin with, because it was from another class. It's irrelevant for us. So I'm going to type in 1 over x. Just a 1 over x. All right. We could go and take a look at the graph if we want, but we're not going to. You'll see above graph, you see a table. All right. In blue here, it says table. If you hit second graph, it'll bring up a table of values associated with this equation. All right. So second graph. Now, the default setting, I regret not setting this up. Pretend nothing to see here, because your calculator should be set to the default. So none of the stuff that I just did should be relevant to you, at least not yet. I'll show you how to do all that stuff, but now's not the time. So fresh screen, you type in y equals 1 over x, you hit second graph, you go through your table, you see numbers, but then you see an error at 0. All right? You see numbers everywhere else, but you always have that error at 0. All right, so I'll do it again real quick. So I'm just gonna freshen up my calculator here, right back to scratch, because I had things changed from other classes. So you hit the y equals key. You put in the expression 1 over x. To get the table of values, you hit second graph. All right. Remember with the TI, for those of us that are getting used to this for the first time, you never hit keys simultaneously. It's always one after the other. All right. So if it's second graph, it's never hold down second and graph. It's always second, release second, then hit graph. All right. So then when you get into that table, you scroll around and you see that there's only an error at 0. And then you look at it and say, okay, it must be an excluded value at 0. All right. So I'm going to do the same thing for a radical. So I'll go into y equals. I'll clear this out. The clear key is a very good option for that. The clear will wipe out an entire row, whereas delete will wipe out just one character at a time. So the square root key, you see that power of 2, x squared? Second that, and then the x key, again, right next to alpha, xt theta n, that's the key you hit for the x. So we have a right arrow to get out of the radical. So now I have a radical x in there. Go back to the table, and you see a whole lot of error for the negatives. All right, always negative for the, always error for the negatives. But then once it's non-negative, once you hit 0, you start getting numerical answers. They're not pretty, but they're numerical answers, right? So you know you're in the right neighborhood. But also it helps you figure out that, okay, this function or this expression is probably good only for x values that are 0 or greater, right? So we would exclude all the negative numbers, right? So that's what all of this is really talking about. Now, I gave it to you in the quickest way possible, but we'll look at some examples just so we can kind of drive the point home. But that's the gist of it. All right. So, the first example, consider the expression x minus 5 over x squared minus 9. All right, I've considered it. Yeah, like I always hated that way of, introducing a problem. It's just so weird. It's very textbooky, but that's how they'll say it on the Regents. They like to use suppose a lot too. But anyway, consider the expression. Is it permissible to let x equal 6 in this expression? So if you're using Desmos, what you can do is type that expression in, just as you see it. Make the fraction x minus 5, x squared minus 9. You're going to see a funky expression. It's going to look crazy. All right? But then just drag along until you get to 6 and see if it brings back a point. Doesn't matter what the point is. As long as it brings back a y value that goes along with the x value of 6, then it is permissible. All right? That's if you want to use tech. All right? TI is not much different. You still type the expression in. So y equals. All right? But the thing is, you remember for fractions, it's kind of a pain. Alpha, y equals n over d. Option 1 for the fraction. Then you type in your x minus 5. X squared, so x followed by that power of 2, x squared key, which is right next to the comma, then minus 9. All right, so you have this expression. You can look at the table or you can look at the graph. It's up to you. It's easier to look at the table. All right, if you hit second graph, you go right into the table, scroll on down, just make sure there's a y value for the x value that you're asked about. If there is, then it is permissible to let x equal 6. All right? And the benefit of having a table is that you can answer multiple questions all in one shot without having to work it out algebraically or numerically anyway. All right? Something else on Desmos, it will create a table for you. It's just kind of not as user-friendly. If you hit that little gear icon right here, so right next to that double down arrow, right above the X, that little gear, you'll see an image of a table. If you tap on that, it'll give you a table of values. All right? It'll be incomplete. It goes from whatever it wants to whatever it wants to. So -2 to 2 is what it wants to. If you wanted to go to, in this case, 6, you would type in 3. It'll recognize the trend. You just keep hitting enter until you get to the number you're looking for. The problem with this approach is that, well, maybe there's nothing wrong with the approach. I don't know. Maybe it's a failing in my understanding, but I don't know how to get it back to the equation except to hit undo a bunch of times. So if you took a lot of time to type in an equation or an expression, You might get really aggravated if you kick it over to a table and then you have to type the whole thing in again, right? So that might be annoying, all right? But if you just need the table, then you could just do this and it's fine, all right? So I'm going to leave it like this because that's all we actually needed for this problem anyway. So let's do it manually real quick. Is it permissible to let x equal 6 in this expression? Well, let's look at it from a different perspective. Back to number 2 here. What types of mathematical expressions would yield an error on your calculator? Those are the ones that lead to excluded values. All right? Fractions with variables in the denominator. All right? In those instances, what you do is you set the denominator equal to 0 and solve for x. All right, most of the time it's x. Solve for the variable. That will give the excluded value or values. All right, we'll worry about radicals in a couple minutes, one thing at a time. All right, you set your denominator equal to 0 and solve for x. So here I'm looking at x squared minus 9. Now we've only worked with linear equations. So we're getting to a point where we're starting to graduate to a little bit more complicated stuff. But it's not really that bad because we're still going to use properties of equality, except we're going to throw in a new one. But in theory, I mean, best laid plans, of course, but that calendar activity, I mean, you've worked with 4 basic operations: addition, subtraction, multiplication, and division, but you also worked with powers and roots. So you kind of hopefully refresh your memories a little bit on that. So if you wanted to solve an equation that looks like this, so it's a 2-termed equation with a power of 2, you'd still isolate the variable using the addition property of equality if you needed to state the approach that you're using. That would give you x squared is equal to 9. To get rid of a power of 2, we want to do an opposite operation. Like if I wanted to get rid of a sum, I would subtract. If I wanted to get rid of a product, I would divide. If I want to get rid of a power of 2 or a square, I would take the square root. All right. The only thing you got to be careful about here, x is equal to, I say what's the square root of 9, you most likely, in most cases anyway, will say definitely 3. Well, actually, everybody should say 3. I'm hoping that most people would also say, what's the other square root of 9? Because there's 2 of them. 3 and it was worth a shot. -3. Because -3 times -3 is also 9, right? 2 negatives cancel out, make it a positive. All right? So that's an extra layer that maybe you didn't have to worry about in the past, but now we got to worry about it. All right? So we have -3 or +3. Now this symbol here, that V, that means or. Feel free to write the word or if you want. It's just nice to know some mathematical notation. If any of you are into programming or would like to be into programming or any kind of discrete math or anything along those lines, you don't know what you're interested in yet, so just keep an open mind to the different notations.
Wait, why is it negative? It could be negative or positive, isn't it? Because since we added 9 to both sides, wouldn't it be the answer be positive?
Well, that's the thing, because you're taking the square root of 9, we would want to be thinking of 2 numbers that are the same that multiply to 9. 3 and 3 work, but also -3 and -3 work. You got it. All right. So these are the only 2 excluded values. All right. So -3 is excluded. +3 is excluded. But that's it. All right, everything else would be included. Right? If something's included, permissible, I mean, I said permitted, a variation of the word permitted is permissible. So there you go. All right? So excluded is not permitted or not permissible. So if I'm telling you that the only ones that are not permissible are -3 and 3, then everything else must be permissible. So is it permissible for 6 to be in the expression? Yes. Is it permissible for 5 to be in the expression? Well, it's not a -3 or a +3, so yes. Is it permissible to let 3 be in the expression? No, because that's one of the excluded values. And give all the values that are not permissible in the expression -3 or 3. All right. So it's a little extra work if you're doing it algebraically, but it's very doable. It just takes time and patience. And I'll tell you that really, as time goes on, the only thing that people will ever lose sight of, that I mean, the process of subtracting and taking roots, that won't be an issue. The only thing people lose sight of is the remembering that there's a negative square root also. That's it. At first, it's studying. It's extra studying. It's like, oh, dang it, I forgot again. Oh man, how many times am I going to forget that? But then eventually, it becomes second nature, to the point where you start wondering if the answer is not negative, why that's the case. All right. So let me do one that involves a radical. If I even have one, let me just take a look. Did I not? Oh, okay. Strike that from the record. Let me do one that's more complicated. Slightly more complicated. So number 4, and this is the last one we'll do, and then I'll let you get going on practice and all that good stuff. All right. So, well, actually, no, I'll do number 5 also. Sorry, because I want to solve an equation with you as well. So, what expression or what values will make the expression undefined? Well, we have 2 factors here. So I want to determine what value or values will make the bottom of this fraction equal to 0. So what I would do is set each factor of the denominator equal to 0 and solve. All right. So at first, it's really the same as saying x squared minus 16 times x minus 9. Sorry, I missed the x. Is equal to 0. All right. That's actually your first step, but that allows you to say x squared minus 16 equals 0, or x minus 9 is equal to 0. All right, that's a weird step, but it has everything to do with what we call the zero product property, but even that's just naming something that may not have meaning. If you multiply by 0, the result is always going to be 0. All right, so in order to get a result of 0 here, so for this product to be equal to 0, it really didn't matter which one of these was equal to 0. It could have been this one that was equal to 0, giving this expression, leading to this equation. Or it could have been this one that was equal to 0, that was supposed to be green, sorry, leading to this equation. All right? Either one of those being 0 would get the job done. All right? So if I tell you that, just as a general rule, if I'm telling you that A times B is equal to 0, then it follows logically that A could be equal to 0 or B could equal to 0. All right? It's a general rule. But the more you think about it, the more you realize it's not a rule you need to memorize, because it's something that should actually make sense. All right? If I tell you that 2 numbers are equal to 0 and the first one is 5, what's the other one? You'd say 0 if you're multiplying. If I tell you that 2 numbers multiply to 0 and the first one's 0, what's the second one? You say it doesn't matter. All right? Because either one of them could be equal to 0. All right. If I were to say this might be even better, two numbers multiplied is 0. Do they both have to be 0 for it to be a true sentence? No. Because as long as one of them is 0, you're good. All right. And so that's what's happening here. So the one on the left, we solved the way we did on the last page. Add 16. We get x squared is equal to 16. We take the square root of both sides. All right, so we used the addition property of equality followed by the square root property of equality. All right. If we had to write it out, that's what we would write. What did we do to both sides? Throw on property of equality at the end. All right. So x would be equal to, well, we know the 4, right? But what's the other one?
-4.
-4. You got it. All right. X minus 9 equals 0. That's easier. That just gives you 9. All right. So for what values of x will the function be undefined? 4. Well, I'll say now. I'll put it in order. 4. I don't know why I said 4. -4, 4, or 9. All right. Any of those three would make it undefined. Now, the algebra can be a little crunchy. We don't want to get bogged down with algebra all the time. If a question says to do something algebraically, you have no choice. You got to do it, but there's nothing to stop you from knowing what the answer is supposed to be going into the problem. So type it into Desmos. The original expression. Oops. Then look for excluded values. But if you can pick out excluded values from this graph at this stage of the game, then congratulations. You're better than I was when I was a student. So we'd want a different approach, slightly different approach anyway. I'll show you that in a sec. But I also wanted to mention that yesterday I said, with Desmos, you look at simple problems. You say, I'm never going to use Desmos, and then later on down the line in the course, you say, oh, this Desmos thing might be good. I don't know that a lot of you expected it to be the very next day, but this might be the moment for you where you're like, all right, let's see about this Desmos, because you may not want to do this all the time. All right, so hit the little gear icon, go to the table, expand your table, and look for errors. So 3, 4, oh, I got an error. I got an undefined anyway. At 4, keep going.
So undefined is another way of saying error.
Exactly. The only issue that you're going to run into with Desmos is, especially if you're using a touchscreen, is just going backwards. Trying to get it, well, also if it's a touchscreen, it's just kind of a pain in the, to toggle back and forth, but there's no up arrow. So if I wanted to go back to like -3 and so on, I'd have a hard time. So I'd have to continue down here to get to -3. But then we run into that problem, So I do -3, -4. Oh, I see. There it is at -4. Bottom line is you got to type it in, all right? Whereas in the TI, you can put in your original expression. I mean, there's a lot to type in. It's not fun. And anybody who ever gets bogged down with the TI calculator almost always gets bogged down because of the typing in part of it. That's just like, I don't want to do it because it's a pain to type it in. All right. Oh, that was supposed to be 16. It's nice when I prove the point immediately. X minus 9. All right, so you type it in, but once you type it in on the TI, then the hard work is over. Because then you just hit second graph and go to your table and just start scrolling around, right? So, just scroll around a lot to make sure. But I see that the first issue here happens at -4, first error. Second one happens at +4. and the last one happens at a positive 9. I will have to show you what'll happen when you have fractional excluded values, because that makes things a little bit more interesting. But for now, that's a pretty good strategy to follow. All right. So for number 5, it's all about equations. So consider the equation. All right. Considered. Find the excluded value of x that leads to the denominator of 0. Fortunately, there's only one expression here that has a denominator involving a variable. So that's the only one I'm worried about. So x minus 4 equals 0. Add 4, you get x equals 4. All right, so that's my excluded value. All right, excluded value means that the number's not in the set, it doesn't belong there, pretend it doesn't exist. So what that means is if I go ahead and solve this equation and I get that number, I can't possibly be right. All right, so start off with the original equation. Pick your favorite method for solving. It is a proportion though, and most folks like to go with the good old-fashioned cross multiplication when it comes to proportions. Remember, cross multiplication only works if it's a single fraction equal to another single fraction. If you have something added on, if it said 2 over 3 plus x on the right-hand side, as a separate item, you'd have to combine first. That's a different story. All right, but this would become 3 times x is equal to 2 parentheses x minus 4. Distribute. Subtract the 2x from both sides. And you get x equals -8, which is a valid solution because it's not the excluded value. All right? So what we're saying is, going into the problem, you look at number 5, and by the way, we did all of number 5 before I finished explaining the theory behind number 4. That's how easy the process can be. All right? So, but going into number 5, the first part is saying, all right, let's find all the bad numbers. Any bad numbers. Then once we find those bad numbers, we say, okay, if any of these numbers come up, we say, forget it, it can't be right. Right? It's almost like you're saying, okay, no way is the answer 4, because that's impossible. And then when you solve the equation, as long as you don't get a 4, you're like, all right, good, we didn't get a 4, we're solid. We got the -8, we're good, we got our answer, moving on. If we got a 4 for part B, we would dismiss it because it's an excluded value. It shouldn't be there. All right? If we got a 4, we would say there's no solution. All right? Because it shouldn't be a 4. All right? There's a contradiction. All right? So, on the Desmos, or the TI, or whatever, the calculators, we know that we could solve equations by writing the left side in as one equation. This is day 3 of me explaining the same concept, so if you didn't like it days 1 and 2, maybe you'll start to like it now. I don't know. Maybe you'll never like it. Look for any intersections. All right. Sometimes it's hard to see because it looks like it might intersect eventually, but they're actually what we call asymptotes. That's a fun word. Bottom line is it's telling us that those graphs are going to run closer and closer together, but they'll never actually touch. But it's the kind of thing that you won't really explore for a couple of years. But we do have a defined intersection point over here at the x value of -8. All right. If the point exists on Desmos, then it exists as a solution. All right. You don't have to worry about it being an excluded value. All right. In fact, the excluded value is over here around or exactly at 4. So it's in the excluded values in this neighborhood. All right. Over here. We got an answer over here, so we're in good shape. All right, we're in business. All right, so that ran longer than I had planned. Through no fault of yours, just I got it on a roll. All right, so consider the equation given. Find the excluded values of x that lead to a denominator of 0. So what we would do is look at our equation, take note of any unique denominator. Right? If it's represented more than once, you only write it once and disregard any other repetition. All right. So just like we did before, I'm going to take that denominator and set it equal to 0. Except in this case, we have a much simpler equation to work with. All right. Whole lot easier. Add 2, and you get x equals 2. So that would be my excluded value. Only one of them. Then it says solve the equation for 0. All right? So we have to keep in mind that 2 is a bad number. All right? Bad number. So when we solve the equation, if we get a 2, we have to say, well, it can't be 2 because we already said 2 is a bad number. So we would have to say no solution. All right? So this is the poison apple. All right? Get rid of it. If 2 comes up in the solution, dismiss it. Get rid of it as fast as you can. All right? So we keep that in mind. We say x plus 3 over x minus 2 is equal to 5 over x minus 2. Now it's a proportion. Most people like to cross multiply when dealing with proportions, so that's what we'll do. So when we cross multiply, and honestly, there are easier ways to do it, but I'm just going to kind of go with what most students would do. And so, spoiler, if you multiply both sides by x minus 2, the x minus 2's cancel out, and it becomes very nice, but let's just play this out. You got x plus 3, x minus 2 is equal to 5 parentheses x minus 2. It's when you get to this step that you realize that you have a common factor on both sides. All right? So at that point, you might realize, okay, well, what do you look for when you're trying to find equality? You're looking for the differences from one side of an equation to another. All right? So I'm not worried about the x minus 2. The equation there is balanced. All right? So if I want to solve this equation, I would want to know what value of x in x plus 3 would equal to 5, because x minus 2 is already equal to x minus 2. All right? Or you could kind of sort of double back and say, all right, well, what do? I can divide both sides by x minus 2, and then you'd be like, oh, wait, I just did that. That's kind of where we started. But if you divide both sides by x minus 2, you'd say, oh, they cancel on both sides. Either way. So even if you don't pick up on it immediately, you'll pick up on it after the fact anyway. So x plus 3 is equal to 5. Then I'd subtract a 3. And I get x equals 2. But x equals 2 is the excluded value. It says it right here. Excluded means bad value. It means that it doesn't exist in the expression. It's not a real location on the graph. So what I'd have to do is dismiss this, right? This is the excluded value. I already wrote excluded value, so I'll say dismiss this. And so therefore there is no solution to this equation. All right. So you'd kind of look at it and say, well, how can I verify that going into the problem? It's the same technique we were talking about yesterday and the day before. Put the left side in as one equation. Put the right side in as another equation. See where they cross. All right. So y equals, maybe you didn't like this technique yesterday, but maybe this technique will make all the difference going forward. Who knows? You'll find out. You'll decide. So left side, right side. Now you look everywhere for where these two graphs will intersect with one another. You might try over here, but as you zoom in, you see that they're close, but they're not actually touching. And you'd say, okay, well, what about over here? No. What about over here? Keep scrolling down, looking for an intersection. No, they're still not touching. No, no, no. And then you say, okay, well, let's cut to the chase here. Let me zoom down a lot, or scroll down a lot, I should say, like to negative 500, and then I'll zoom back in and see. Dang it, they're still not touching. And if I do the same thing going upward instead of downward, you'll see that they actually never touch. These two graphs will never come into contact with one another. And yeah, we're a little, it's kind of stealing my own thunder, but we're not there yet. But two graphs that approach each other but never touch, they're called asymptotes. That's what we're dealing with here. So if you see anything that's in this form where you look at two graphs that seem to merge but never touch, you're not going to have a solution. There's not going to be an intersection because they're going to be asymptotes. Right? It's a weird word, but that's exactly what's happening there. Right? So that's the solution, and the solution is there is no solution. All right? So